Welcome, everyone, to today's session. We are here to discuss one of the most critical aspects of modern cloud-native design, securing service-to-service communication in Kubernetes. As we move away from monolithic architectures into distributed systems, the complexity of securing the network increases exponentially. I have titled this talk, The Architect's Journey, from Application Control to Infrastructure Trust, because it highlights a fundamental shift in our approach. We are moving from a world where developers had to bake security logic directly into their code to a world where security is an intrinsic part of the infrastructure itself. Today, we will explore this evolution and how you can establish a robust foundation of trust for your services. In a distributed microservices architecture, we must operate under the principle that every service is an island. We can no longer assume trust based simply on a request's network location. Instead, we must verify every single interaction. This zero-trust approach is built upon three critical pillars. First is identity, which addresses how a service proves it is who it claims to be. Second is authorization, which determines if a specific service is actually permitted to perform a requested action on another service. Finally, we have integrity, which ensures that a request has not been tampered with while in transit. Together, these three elements form the foundation of a robust security model for modern service environments. Pattern 1, known as the Application Layer Fortress, focuses on building security measures directly into the application logic to achieve maximum control. In this model, the service itself takes responsibility for terminating TLS and validating identity. As shown in the diagram, Service A begins the process by performing an MTLS handshake and certificate validation with the token authority, which is implemented here as a Rust application. Once identity is verified, the token authority issues a Pasado token back to Service A. Service A then includes this Pasado token in its API calls to Service B to authorize the request. This architecture leverages three key technologies: Rust for its inherent memory safety and strict type system, MTLS for robust cryptographic transport security, and Pasado, which provides a modern and secure token format. By handling these security concerns at the application layer, we ensure a high degree of precision and security for internal service-to-service communication. Building a foundation of modern, secure technologies requires a multi-layered approach, starting with the programming language itself. By using Rust, we leverage its inherent memory safety and strict type system to eliminate entire classes of vulnerabilities that are common in other languages. At the network layer, we implement application-level MTLS. This enforces cryptographic identity verification directly at the process boundary, ensuring that an attacker on the network cannot even establish a connection without a valid client certificate. Finally, we utilize Pasado v4.public as a superior alternative to JWT. It employs strong ED 25519 signing and is inherently immune to algorithm confusion attacks, which guarantees the long-term integrity of our tokens. To implement the token authority in Rust, we start by defining our key dependencies in the cargo.toml file. We are utilizing Axum as our web framework, along with Axum Server, specifically configured with the TLS Rustless feature to handle secure connections. We also include the Passators library for secure token management. Moving to the implementation in main.rs, we initialize our server configuration using Rustless config. As you can see, the configuration loads the server certificates and private keys directly from the local file system. The most critical line in this setup is the call to test only allow client certs true. This specific configuration enforces mutual TLS, or MTLS. By enabling this, the server will strictly reject any connection request that does not present a valid client certificate signed by our trusted certificate authority, providing a robust layer of security for our service. This process demonstrates how we transition from a verified certificate to a scoped token within the handler. There are three key stages involved in this conversion. The first stage is identity authorization. Assuming the MTLS handshake has already successfully completed, we inspect the subject of the peer certificate to ensure the caller is permitted to request a token. For example, we check if the service identified by its common name is authorized for this operation. Next, we create the Pasado claims. We build a payload that asserts the identity of the caller and includes a short expiration period. Crucially, this is where we add custom scopes to enable fine-grained access control. In the provided example, the subject is set to Payment Service, and a Write Billing scope is added to define specific permissions. The final stage is signing the token. The claims are signed with the authority's private key using the v4.public standard, which leverages ED 25519. This resulting token contains a public payload but is entirely tamper-proof, ensuring that the identity and scopes cannot be modified while in transit. This slide explores two key technical advantages: custom claims and implicit assertions. First, let's look at granular authorization through custom claims. Because the token authority is application-aware, it can embed rich business context directly into the token. As illustrated by the examples, such as tenant ID, user level, and specific scopes, this shifts authorization logic from a simple identity check to a more powerful model. It answers not just who is accessing the system, but who, on behalf of what entity, and with what specific permissions. Next, we address security through implicit assertions to prevent replay attacks. An implicit assertion is data included in the signature calculation, but omitted from the actual token payload. This requires both the signer and the verifier to have prior knowledge of this data. For instance, if a token is tied to internal API v1, an attacker who steals it cannot reuse it against a public gateway v1 endpoint. Even with the correct public key, the validation will fail because the implicit assertion does not match. This effectively binds the token to its intended context, providing a robust layer of protection. We find ourselves facing the architect's dilemma. While we have designed a powerful and secure solution, we must carefully consider its operational complexity, operational burden, and a common source of outages. Next, we encounter the bootstrap problem. Determining how a service initially authenticates to the token authority is a challenge. While using Kubernetes service account tokens is a strong approach, it adds a necessary but complex layer of validation logic. Finally, there is the issue of code overhead. Every service must now incorporate middleware to validate Paceto tokens, verify claims, and manage the authority's public key. This increases the development and maintenance requirements for every service in our environment. Pattern 2 illustrates the infrastructure alliance with a service mesh. This model allows us to offload critical tasks like transport security and identity verification to the platform itself, which greatly simplifies our application code. Looking at the architecture, we have Service A and Service B, each running in its own pod. Every pod includes an application container and a dedicated sidecar proxy. Within the pod environment, the application communicates with its local proxy using simple plain-text HTTP over localhost. The complexity of security is handled entirely by the service mesh. As data travels between the pods, the sidecar proxies automatically establish mutual TLS, or MTLS. This ensures that all traffic in transit is both encrypted and authenticated without the application ever being aware of it. By shifting this responsibility to the infrastructure, the application no longer needs to manage TLS certificates or logic. We can achieve comprehensive encryption in transit with zero code changes, allowing developers to focus solely on core business functionality. In this architecture, we observe a fundamental shift in the trust boundary, moving it from the individual process to the pod level. Instead of the Rust application performing its own cryptographic handshake, the Envoy sidecar proxy takes on this responsibility. When a request arrives, the sidecar verifies the caller's certificate and then forwards the validated identity details to the application container via an HTTP header, specifically the X-forwarded client cert header. This header provides the application with necessary context, such as the subject name and the SPIF ID. However, this transition introduces a critical security dependency. The application is now trusting a text-based header rather than performing a direct cryptographic verification itself. Consequently, this model is only secure if the environment is configured to ensure that this header cannot be spoofed and that all incoming traffic is strictly routed through the sidecar proxy. To guarantee header integrity and secure our model, we must ensure that only the local sidecar proxy is permitted to send requests to our application container. This can be achieved through two key mitigations. First, we bind the application server to localhost. By configuring the application to listen on 127.0.0.1 instead of 0.0.0.0, we make it unreachable from the broader cluster network. This prevents malicious actors or other pods from bypassing security controls to send forged XFCC headers. As shown in the diagram, while direct network traffic is blocked, local traffic from the sidecar remains permitted. Second, we enforce strict mesh MTLS using an Istio peer authentication policy. By setting the MTLS mode to strict, we mandate encryption for all incoming pod traffic. This ensures that the sidecar proxy rejects any plaintext or non-MTLS requests before they can reach the application. Together, these methods provide a robust defense-in-depth strategy for maintaining the integrity of our internal communications. The application's role evolves into being identity-aware without being operationally responsible for the underlying security infrastructure. Instead of implementing complex TLS termination logic within the code, the application simply uses a middleware to parse the trusted X-forwarded client cert, or XFCC, header. As shown in this code example, the middleware extracts the caller's identity by parsing the header injected by a trusted proxy. The parsing logic specifically targets the SPIF URI field. This is a critical best practice because the SPIF URI is the industry standard for defining workload identity in Kubernetes environments. By offloading TLS termination and certificate management to a dedicated infrastructure layer, the application's security responsibility is reduced to simple string parsing. This allows developers to focus on business logic, while the platform handles the heavy lifting of managing cryptographic keys and certificates. This decision framework provides a side-by-side comparison between a custom Pasado authority, dubbed the Fortress, and Service Mesh MTLS, referred to as the Alliance. Starting with the security model, Pasado functions at the application layer using tokens, while Service Mesh MTLS operates at the network layer using certificates. In terms of code changes, Pasado requires significant effort as every API needs built-in logic to verify the tokens. Conversely, Service Mesh MTLS requires no changes to your code, as it is managed transparently by the sidecar proxy. Key management represents another major differentiator. With a custom Pasado approach, management is manual, requiring you to handle the rotation and distribution of private and public keys. Service Mesh MTLS automates this process, handling certificate rotation frequently and without manual intervention. Lastly, we consider granularity. Pasado offers high granularity, enabling the inclusion of rich custom claims like user IDs and specific scopes. Service Mesh MTLS is limited to service identity. It confirms which service is initiating a call, but lacks broader application-level context. To reach a verdict on our security architecture, we must match the right pattern to the specific problem at hand. We generally weigh two options: building a custom Pasado authority or utilizing a service mesh with MTLS. Starting with the service mesh approach, this should be your superior default choice for operational simplicity and robustness, rich application-specific context. This pattern is necessary when your services are acting on behalf of a specific user or tenant, or when you require the enforcement of fine-grained permissions, like a specific write capability. It is also the correct choice if the token itself must carry auditable business data. Ultimately, while the service mesh handles identity at the infrastructure level, the Pasado authority allows us to embed deep user-centric context directly into our authorization flow. Aligning security with your true requirements is fundamental to creating a resilient and sustainable system. Often, we fall into the trap of thinking that more security code equals better protection. However, the most effective security architecture is not defined by the sheer number of layers in your application code. Rather, it is the one that intelligently leverages the capabilities of the underlying platform. By placing the trust boundary at the most logical and manageable point, we reduce complexity and minimize the attack surface. A key principle here is knowing where to exert control. You should choose application-level control specifically when you need the deep context that only the application can provide, such as specific business logic or user identity. For all other security concerns, the best approach is to build an alliance with your infrastructure, allowing the platform to handle tasks like network isolation and resource access at a lower, more integrated level.